and some local organization or another comes out a couple times a year and they clean up all the trash on the side of the road for 2 miles or so, right? So we saw at the end of the film some ideas for removing space debris, and I'm wondering, could we just create a, I don't know, an adopt an orbit kind of program and have organizations help with cleanup? Or maybe what are some of the gaps in international space law that have made orbital debris a bigger challenge than just a technical one?
Okay, so whenever I do talks, usually, I start off by saying, to introduce myself, that a Canadian, British, Nigerian space lawyer walks into a bar. And everybody starts laughing because they're like, yeah, it sounds like a joke, but it's actually true. I exist. So essentially, it's really interesting because when we start talking about these technical issues, space debris, and you see all these different solutions that people have, it's very interesting because a lot of the challenges are actually political, right? When you decide what are you going to do about these actions, it's an issue of international diplomacy. So it depends on what countries want to do. And at the end of the day, they love the fact that they have a lot of free reign to do the things that they want to do. And so nobody actually really wants to be limited in their activity. So it's really interesting when people talk about the Chinese ASAT test, right? You would think, Article 9 of the Outer Space Treaty talks about harmful interference. And so, that's the closest we get to some kind of environmental protection provision. But even that, states have decided that that does not amount to harmful interference. So you can imagine, and we talk about that Chinese ASAT test as if they're the only ones. Like in the 1990s, US also did an ASAT test, which also caused debris. The interesting thing is that after the Chinese test happened, say maybe like 2 weeks later, the US now did an anti-satellite test of its own, but that didn't cause any debris, to show you the right way that it's being done. So everything ends up being kind of politicized, right? So I think the challenge is also, so in law, we do have law that applies to space. So when you say, okay, what is a space lawyer? So there's generally like 5 treaties that everybody knows about that specifically apply to the space context. The Outer Space Treaty is like the Magna Carta of space law. That's the general principles of space law. But under Article 3 of the Outer Space Treaty, it says that general international law also applies to space. So then we can say actually all laws apply to space. So when people say there's no law, they're not really right. The problem is, how do you apply those in the space context in the presence of politics and diplomacy? So that's usually kind of the challenge with a lot of these things. The second thing is also the problem of definitions. Now, as lawyers, we spend a lot of our time defining things, but you want to define things as loosely as possible. So even a problem of saying, what is space debris, is a problem because there's no definition of what space debris is. When does something actually become debris is a personal determination of a specific country because they retain jurisdiction and control over their space object forever. And there's no such thing as abandonment in space. So you can't say that Russian satellite that was dead is defunct, so it's now abandoned so someone can go and clean it up. No, that constantly for its whole lifetime is, whether it's functional or not, is the jurisdiction and control of the state of registry, which is the state that registered that object. So these are some of the challenges, and so even when you do, the closest thing that we've come to, which is the soft law principles, which are things like the non-binding resolutions we talked about, which are non-binding agreements, as everybody wants them to be soft law so people can decide how they actually implement it. So I started my career at the Nigerian Space Agency. So for developing countries, it's always like, well, look at all these people who've been able for years to do what they want, and now you're going to put all these barriers on us. So you always have these political issues too, where people say, how are you going to tell me what I can do? So that's always a challenge as well, balancing the politics of this all. So it's actually more a political issue, I would say, than really a technical one.
All right, thank you for that, Timmy. Jehan, you brought some of your CubeSats here to show us before the movie got started. I wish we had one up there now, but it's what, the size of a shoebox maybe. They're really small. Can you talk to us about what unique problems CubeSat pose for space traffic control and space situational awareness?
Sure. At the moment, with the CubeSat standard, there is no specifics about deorbiting or a plan for deorbiting. That's still up to a program that you want to then apply to, where that's really a shelter of guidelines. So that, from an engineering point of view, I think opens up opportunities. All of the challenges that were talked about, I think has engineering opportunities to readily solve. These are not, I would say, issues that are intractable as other issues that we face on Earth. And so this is something that's still somewhat early stage that we have a chance at, I think, simpler engineering solutions to going after a lot of these things. But there are still some challenges also in terms of law and such. So there are, I would say, preemptive methods that could be used. For example, if you're going to be launching a CubeSat, you have a deployment system in the CubeSat that, in a sense, is that parachute to cause it to deorbit and assure that 25-year guideline wherever or whatever altitude it is in. And then there are other possibilities too. I think the possibility of dealing with smaller pieces of debris, the so-called secondary debris that's formed that could be either collected or in other words gathered. I sort of see that with the amount of material up there, particularly in geo, that in fact has a basis for reuse and easy access to being enabling reuse than perhaps going out to asteroids and doing space mining. In fact, there's enough resources there that you could start to reuse to create your own second-hand satellites, say. And so I think for every challenge we've talked about, there's an equal and opposite opportunity that could be figured out. And I'm sort of still in the sort of the big sky sort of paradigm in that it's not down and dangerous yet. But this is also an opportunity where internationally we can come together to come up with rules and I would say good behavior clauses that could help prevent an oncoming catastrophe that could end up just being expensive to deal with in the long run. And so this could be another testament to global cooperation.
Just as a quick follow-on for you, are there technologies that you're thinking about as you design your CubeSats that make them perhaps inherently more trackable? You're putting beacons on them or making them irradiate in some way that it's easy to know where they are?
Yes. We're looking at CubeSats. CubeSats definitely large enough that the de facto Space Traffic Management Agency, which is called JSPOC, can track them. Their limit is at around 5 centimeters by 5 centimeters by 5 centimeters. We're also looking at satellite designs that are smaller than 5 centimeters. That's both an opportunity and a challenge. In that realm, you do have to have technologies that give you one easy ways to sort of enhance or enlarge the volume. So we've looked at inflatables, inflatable technology that uses kitchen chemistry, as we call it, things like Tylenol or acetic acid, and you take them as powder into space, and that powder turns into a gas, and it produces enough gas to last for years that you can just create this inflatable without having to carry high pressure pressure vessels, which is just a lot more engineering hassle. And so with that technology, you can have something inflated that take up a large area that it could be visibly trackable or large enough for multitudes of technologies to be trackable. So that's why I sort of feel that for every one of these challenges there is an equal and opposite opportunity, and in fact, and many times low-tech engineering opportunities out there.
All right, thank you all. Who from the audience has thought of a question they'd like to ask? Saw this hand first over here.
So considering the total number of objects that are out there in various orbits and planes, I guess you would call them, what's the likelihood if you launch a spaceship, typically like the ones we do now, that there's going to be an impact of, let's say, 1 centimeter size object on that spaceship? And are there specific corridors which are less populated by things that we can see and can't see that are employed in order to minimize that? Who wants that?
Works? Okay. Well, it kind of depends really where you put it. So, for instance, as we saw, like the International Space Station, like has specific provisions to protect itself from like 1 centimeter impacts. That's definitely not negligible. But also, like the International Space Station is a very valuable asset. Most of the times, as far as I know, the satellites that are put in orbits that are 800 to 1,200 kilometers. That's let's say 750 miles from the Earth. That's a pretty crowded region, but I don't think that those satellites are usually protected. Like I don't think they're engineered to withstand those types of impacts. Also because most of the times, I mean, 1 centimeter can be non-lethal. Usually it disables the spacecraft, but it also depends what it goes through. But I can give you that, like the exact probability is actually kind of a challenge to say. It's definitely non-negligible and actually might already be happening, because we're seeing, for instance, battery explosions in orbit, and when you see that a satellite doesn't go silent and you see a little cloud of debris coming out, you know it's probably battery explosion. But there's speculation that maybe if a debris goes through a battery, that's what causes the explosion. So it might already be happening. We know exactly the probability, but it's definitely there.
And of course, we don't all completely understand all of the forces that are acting on those objects, right? We have Earth's gravitational field that we know pretty well, but you've got the sun and the moon, and you've got coronal mass ejections and the solar winds that can blow things differently, right?
Yeah, exactly. There's also, that's a problem actually for satellites that are under 1,500 miles from the Earth. They're still in the region in which there's a residual atmosphere. Modeling the interaction with the atmosphere is very difficult, and it affects how the orbits evolve on time and the quality of your predictions, and ultimately the probability of collision.
I have two questions. One, how is the space debris tracked? Is it tracked with optical telescopes?
Well, I think that the simple answer is most space debris is not tracked.
Okay.
So that makes it simple. Only the very, very larger pieces are tracked. There are about, I was just looking at the box scores out of Space Command this morning, there are about 12,000 cataloged pieces of debris in orbit right now. To contrast that, there are about 500,000 objects greater than 1 centimeter in size estimated to be in orbit by the NASA debris models. So the vast majority of it is not tracked. From the standpoint of the stuff that is tracked, most of the low Earth orbit stuff is tracked with radars, and that's because you only need a few of them, and they work during the day so they can see the small low Earth objects every time they pass over the radar site. So the vast majority of those are tracked with radar.
And the other question is, the Earth is showered with meteorites all the time. how is it that the meteorites enter and come to Earth, enter our atmosphere, come to Earth, but these objects, these space objects, still continue to orbit without falling to Earth?
It's all because of the atmosphere, and that's something that to really understand the debris problem, you need to appreciate the difference between the lower space debris and the things like in geo. And you transition from an environment in low Earth orbit, like where shuttle is, where space station is. Those are about 90, 100 kilometers up or so. They're basically up just high enough to stay there and out of the atmosphere. Those experience a lot of atmospheric drag, and if not reboosted, they re-enter the atmosphere over the course of years, in some cases to a decade at most. Space station would come back down pretty quickly if it wasn't continually boosted back up. As you get up to this kind of 1,000-kilometer altitude, where we have a lot of weather satellites, we have those are kind of special orbits because you can make them go over the same point in the Earth same time every day. Those orbits tend to stay stable for hundreds of years. Early in the space age, we had a set of rocket bodies called delta rocket bodies that did a lot of launches in there, and several years after being put up there, they'd explode, and they'd create, in the order of 300-400 pieces. Because that stuff was at 1,000 kilometers instead of 100 kilometers, that stuff's still there, and that stuff will be there basically for the life of the space age. As you get up to GEO and those graveyard orbits the movie spoke to, that stuff's basically up there forever. If it has any mass up there, that stuff will be there forever. If Star Trek came along, in 10,000 years, they'd still see that stuff still hanging up there, clinging as a relic to our civilization. So the consequences and the time scales vary quite a bit as you go up.
I see another question right up here. Yes.
So many questions, so little time. So I guess the first question I have is that the orbits, the things we track, the things that are trackable, the orbits, we don't have good information on where they are. So the Iridium Cosmos collision happened. It wasn't even predicted to be a bad conjunction. So are two-line elements adequate going forward? And then how big does the space surveillance network need to grow to handle the amount of objects we have in orbit now to have accurate ephemeris on them? Two-part question.
So just to clarify, maybe for the general audience, the true line elements are they're part of what's called the U.S. Space Catalog. It's the largest public database about the orbits of satellites around the Earth that's maintained by the Air Force. And the true line element format is it's definitely not sufficient to do any type of reliable collision prediction between two satellites. And in fact, what the Air Force usually does is to issue what's called, I think, a conjunction data message to the operators, but that's a separate system from the TLEs. The true elements are not that accurate. They're good for population studies, but they're not. They're often not accurate enough to track a satellite long term. That's actually like an active field of research on how to get those and use statistical studies and orbit determination to improve the information that we have. Regarding the sensor network, and maybe Eric is better qualified than me to.
That's a tough question, and you cannot build a space surveillance network that will do that. More sensors are not the problem. To be able to predict satellite's position 1 revolution later, 90 minutes to several hours later, to an accuracy comparable to the size of the spacecraft itself, I think will always be an intractable problem. The adding more data is not going to help. If you look at the NASA, NASA has spent 4 decades, 5 decades, building very, very complicated debris models to do satellite design, essentially, and calculating, what statistically is going to hit my satellite in this orbit. Most threat to a satellite mission is millimeter-sized stuff going splat. You see that when you bring things like long-duration facility back, you count little holes in it. Most of the damage to your satellite is millimeter-sized stuff. Most of the objects on orbit that we can track above 10 centimeters are not maneuverable. So even if you do get conjunction analysis, and even if you did have the accuracy, there's really not a whole lot you can do about it except sit around and worry. I know, and we forget how economically driven it is. Everyone's seen Star Wars, everyone's seen Star Trek. I mean, who pays for the Enterprise? That thing must have cost a few $1 trillion, and they just kind of drive it around, and it doesn't seem to make any money. Space is like that. You see these, let's go remove 10 centimeter debris. Remember, 10 centimeter debris wasn't the threat to the guy who's got the satellite up there. How much does it cost to put a garbage collector out there that's going to meticulously go and get co-orbital with some 10 centimeter piece of debris and pick it up and stick it inside and go take it somewhere else while building that spacecraft and not creating more debris than you're picking up? I mean, who's going to pay for that? That's going to be incredibly expensive. So it all comes back to economy. And, I can't say in a public audience I'm against space traffic management. I mean, who can be against space traffic management? But I guess I'm in academia now, I can say that. Space traffic management only solves a very small part of the problem from an owner-operator satellite getting beat up on orbit. It's a small problem, but it's a very high visibility part of the problem.
I think also interesting to note is that the people who make the most money from space, so like the big satellite operators for like GEO, they also kind of have a way that they deal with these things. So there's the Space Data Association, which is basically like a club of all the big satellite operators who do conjunction analysis between themselves and tell each other about things too. So, it's a great question when we talk about the whole of space, because yes, who's responsible? But when there's a direct bottom line to a specific person, they have these kind of solutions that they use. But the rest of us definitely need to be thinking about, how do we prevent making this problem even worse? But I think a lot of the discussions that we do have about these technical solutions, I think it's a great technical discussion about technology, but it's just not very practical.
My question is nuanced and with utopia a lot, and it's addressed directly to you, because it actually, how about having international prevention negotiations, which means that putting the orbiting instruments on any common satellites, whether they're CubeSats or whether gigantic sats. And it's better to deal with 5 to 13 nations that are in space now than with 50. What do you think?
Yeah, definitely. It's all about international cooperation, and the people who came up with the space debris mitigation guidelines was basically a committee of the big space agencies who said, how do we find a way of communicating what the best practices are? So actually, what we have right now with the debris mitigation guidelines are the best practices as of now. So it's like really the bottom, level of things that are already acceptable to kind of be doing. But what's really interesting about, like I alluded to in the beginning, is that politics gets in the way. I've been to a lot of UN negotiations for the Climate Change Convention, for the space discussions. So many things come into the conversation that is not really kind of the issue at hand. But an interesting thing to talk about space debris, if we want to use politics in a positive way, is that it's really hard to talk about the problem of weaponization of space. and how do we prevent weaponization of space, but we can use the fact that we don't want space debris to try and have a discussion about the politics of should we have weapons in space. So there's a lot of discussions about, obviously if we have weapons in space, that's the biggest debris causing incident because of weaponization of space. So if we try and prevent that, that's like a big source that would, be stopped from space debris. But like I said, the problem is that it's a limitless possibility of things that you can do in space. And, all states want to be able to keep doing what they want to do.
And in fact, even thinking about what weaponizing means that's a whole legal rat's mess too, right?
I think along these lines, there's still not enough, I would say, awareness of this, and it's still limited to the space community and perhaps elements.
To what extent are you polluting the oceans when you have stopped the orbiting and burning up?
The satellite dumping yard, from what I understand. 100 tons of space dust that re-enters and so this idea that is not quite true. And so apart from our own, some apparent take dust on it, then that came from space, and it's everywhere. What is also natural, right? As opposed to
about this, because as far as I know, the last few months have been bought out or into that. I know the Archite satellites were based. Also, just the sheer legality of lines.
Still, a few asteroids out there. There's a DARPA program called FEED. Use them or take parts of in lower. We're going to buy something from who said, we're ready to.
Etc., etc. Concerns me, okay, is that the same bunch of people that have given us 6, not 1, solution of being remediated, are now talking about what to do up top. Lack of progress. Basically, we're still blowing. I find that very surprising. The fact that we haven't gone back to the moon, for instance. Okay? I mean, if you think about the computer that was on board of the Apollo, okay, and an iPhone, I find it very difficult to understand, especially with the tremendous increase in knowledge in material science, okay, why people are talking about it being cost prohibitive. It's astonishing to me.
Want to comment on a comment?
So, go please. Sorry. Just regarding the third. We're still working with technology that's basically root in the 1960s, and that's because in the 1960s, sorry? Yeah, well, I mean, but the reason why that is because in those years, the reason why there was a space race, it was because there were two major powers fighting. Interests, and as of now, as of still today, there hasn't arisen any interest that's as strong as that. Actually, I think that the only player right now that has kind of revamped that kind of interest is China, and missions, and they give like a lot of prestige to the Chinese program, and that's commendable. But so we're talking tenfold. I don't think that we will see of achieving orbital velocities as rockets now. But that's not a question.
I'll just say, as far as visiting the moon or Mars or any other manned mission, Neil deGrasse Tyson published a book a couple years ago called "Unless There's Very Clearly an Awful Lot of Money at the other end of it."
Yeah, so, I got into space from a developing country perspective, and I was working with, we don't even have continuous electricity supply, why do we need a space agency? So like my job was always like, oh my god, how do I make the case for space for. And now obviously I live in Western countries, I go to a lot of discussions, and there's very American-centric notions of exploration, and like people want to go out there, and I'm like, is that really what everybody thinks? Going to the moon, going to Mars, having a settlement on Mars, like for the majority of people that I know, that has nothing to do with them. So we, the space community, have to figure out how to do a better job at explaining, okay, like the video showed, without space, we wouldn't have GPS, we wouldn't have the ability. I think we made a good point here. I think we made a good point here. And
to the precision of about 5 kilometers. Either with the current computing
incentive aspect of it, ever getting to the point where payload insurance is getting so the financial burden of
I think studies to be made, particularly forecast. There is going to be, in other words, that next level, where see, what is salvage value, and the reverse, which is critical communication assets get down on the ground. And type study that could as they used to have, because they listen to those and so there's at the UN where you have on really scientific principles in engineering.
Delta V means changing bombs with capsules on its orbit. All of this people re-enter low Earth objects. And that's why those are feasible. And that's why those are feasible. Cooperation looking forward in the next. The owner-operators sharing. Sitting in one little spot, sharing one company. They all work together very cooperatively. Navigate the satellites around each other. Local opportunity looking, and that's enabled because it's not getting big rockets. It goes back to the business case.
Agree with them. The problem is that you have to now is moving forward. Benefits is, for instance, if we understand more about quantify the level of the risk because we have more.
Thank everybody for being here today in our inaugural.
And regarding that, one regarding reducing the costs of mitigating debris, we're trying to push forward this idea in which there's. So for low Earth orbits, you have the atmosphere that does the cleaning. So eventually stuff will come down and burn in the atmosphere. That usually doesn't happen for higher orbits, unless in some specific regions. It turns out that for navigational satellites and for satellites in GEO, you can exploit gravitational pulls of the sun and the moon to either guarantee that your graveyard orbit where you're putting your satellite will be stable basically forever, or to change the orbit on a scale of like 10 or 20 years so that it eventually goes and collides with the Earth. And it actually, there's been like a fun example of this because there was, I think one of the examples of one of the satellites of the Sirius constellation, which is a satellite radio constellation in GEO. It was, at the end of life, it was placed in a graveyard orbit, so it will stay there forever. But if we found, a colleague of mine found out that if only they had left it there, it would have crashed naturally on the Earth within 10 years. So actually, like, this is a small drop in the ocean, but there are ways right now to understand the environment better and reduce the costs of the orbiting satellites.
All right, good. Well, let's end on a positive note there. Please join me in thanking our panelists today. Thank you all for being here, coming to the University.